Hi everyone. Today we will discuss the application of SDEs in option pricing. This is a very famous topic in quant finance, and let's get started. So let's begin with a probability space, omega, FFT, and P, where FFT is the filtration generated by a Brownian motion WFT. For simplicity, we assume that our market model only consists of two price processes, a stock price following geometric Brownian motion, and then a bound process following a deterministic price process. In our later application, we will assume that this BFT is a risk-free baseline asset. With this market model defined, we then can define what it means to be a European call option. So a European call option of stock S with strike K at maturity T is a right to purchase a stock at price K at time T. So basically, at time T equals capital T. If the stock price is greater than K, then you can earn ST minus K. Otherwise, you will not exercise this option, so you earn 0. Therefore, the terminal payoff structure is summarized by this maximum function. With this terminal payoff defined, the problem of option pricing really becomes determining a reasonable price process Vt S of T for T smaller than capital T. Especially, we want to know the option price for T equals 0. In other words, the current price. And the next natural problem is, what is the definition for reasonable? Well, in finance, a nice criteria for reasonable is no arbitrage. And to define no arbitrage, we need more additional terms. So a portfolio basically is a linear combination of assets. In our model, assets is only S of T and B of T. And a portfolio is self-financing if there's no external inflow or outflow of the money. So if we apply Ito's lemma to pi of t, we can get this expression. So the second term of this expression basically describes the capital inflow and outflow between assets. If there's no external inflow or outflow of the money, this second term should sum up to 0. Therefore, we have this self-financing definition. Second, a portfolio pi of t is called admissible if the payout of pi of t is bounded below almost everywhere. And with these two terms defined, we can define an arbitrage. So a self-financing admissible portfolio is called an arbitrage if you can start with 0 capital, and then you can earn a positive amount of pi of t at time t equals capital T for positive, strictly positive probability. So basically, it is a free lunch. And here's our theorem. So if there exists an equivalent measure Q, such that for all assets, X of T divided by our baseline asset B of T becomes a local martingale with respect to Q, then there's no arbitrage opportunities in this market. The basic idea of this theorem is that no arbitrage property is a almost sure property. So you can basically choose whatever convenient measure space measure you want to work with. And if you can find a measure where everything becomes a martingale, then starting with 0 capital, you can get free lunch at T capital T. And here is a more formal proof of this theorem. So we prove by contradiction, suppose there exists an arbitrage opportunity, then by Fatou's lemma, you can show that the expectation of pi of t at capital T would smaller or equal to 0. However, the definition of arbitrage requires that pi of t greater or equal to 0 almost surely. Therefore, we conclude that pi of t must equal to 0 almost surely. But this contradicts with the requirement where we must earn positive profits with positive probability. And I want to note that the reverse direction of this theorem is also true, meaning that given the market model, if this market does not exist any arbitrage opportunity, then there must exist a measure Q such that X of t divided by B of t are all local martingales. And this is called the first fundamental theorem of asset pricing. Returning to our European option pricing problem, so we have S of t and B of t. B of t divided by B of t is a martingale. Therefore, if we can find a measure Q such that S of t divided by B of t becomes a martingale, we can then define V of t, S of t as the expectation under this new measure Q. And by our previous theorem, this will give us a no arbitrary price of our option. And if we write now the equation for S of t divided by B of t, we would realize that finding this equivalent method is really a matter of applying Gassanov. So writing out this equation out, and you can define the lambda t by this expression. By Gassanov, you can know that there must exist a measure q such that S of t divided by B of t becomes a martingale with respect to the measure q and this new Brownian motion W bar t. And then we define our value of the option as the expectation on the Q of this terminal payoff, discounted terminal payoff. So the next natural question is there any PDE where we can solve Vt of S for any T and initial process? The answer is yes. Remember that we have this Feynman-Cass formula. Well, if F solve this PDE, then FTX could be expressed as the expected discounted payoff of Gx of t. So if we let F equals V, we let R equals constant R, and then Gx of t equals the final terminal payoff of our option. Then knowing that our stock price process, we are now following this new process under the new Brownian motion and the Q, we can find out the generator L for this new Brownian, for this new stock process, and then write down this equation for V. And this is the Nobel warning results of Black-Scholes. Next, Yue Li will talk about more complicated problem of American option pricing.
So I will continue to talk about the American options as the relevant strategies. So the American option allows the holder to exercise the contract at any time before maturity T, whereas a European option allows the holder to exercise the contract only at maturity. So our setting assumes that the market is complete, which means that every payable payoff is attainable at T0, so that we can price any claims if all the claims in the market are attainable. So an important theorem is that the market is complete if and only if it exists a unique equivalence local martingale measure Q. So this is useful in many of theorems below. So the replication of the price of an American option with exercise P of G is it can be expressed by this equation, where pi t at t denotes the set of all stalling times tau that tau belongs to t capital T P history almost surely. And this solution satisfies this equation where L is the Ito generator of T, LT, with this boundary condition. So this variational inequality can be converted into a similar linear PDE, which I discussed below. So the function U belongs to C12 is a solution to this variational inequality if and only if this holds. So to prove this, we can first prove provide Ito's level to G and split it into the exercise region where U equals to G and the continuation region where U greater or equal to G. So by the variational quality, the integral in this continuation region U greater than G vanishes, so we can get a simpler expression. And after some simplifications, we can apply the Feynman-Cass formula to solve this. So another important result that we'll use to formulate the dual problem is this dual decomposition. It means that this process U is this is a Cadillac super martingale, and it means the dual decomposition where MT is the martingale and AT is the non-decreasing process. So now let's go to this dual problem in pricing American options. So the dual method is the second way of valuing American options. The first method is called the Snell envelope, which is the maximization approach, which is this Snell envelope is defined as this. So it quantifies the maximum discounted gain from exercise the option of time t if the option has not already been exercised for a given measure q. Since tau t is a possible exercise strategy, the Snell envelope is always greater than the option discounted payout, which satisfies this inequality. So this is associated with the martingale Q, measure Q, and to the American option factorized pay of the TFT, which this is the discounted factor from 0 to T, and FT is the face value of this option. So the dual problem, on the other hand, it can transform the maximization problem into a minimization one. So now we have this dual problem formally formulated. Then for this empty dot denotes the set of all right continuous martingales with empty equal to 0. It satisfies this equality, so that the right-hand side can be considered as minimizing over all the martingales ms, and we try to find the optimal martingale m star. And the left-hand side is the primal problem, which can be considered as maximizing over all stopping times tau. So this optimal martingale m star is the martingale part of the two-Meier decomposition of this super martingale, which as is the envelope of this counting factor. So we can get the upper bound of this v naught for this value of this medical option at time t, time 0. So to prove this, we have to recognize that we can use optimal sampling theorem because tau belongs to this pi tt is bounded. So, and then we also recognize that the Snell envelope is a super martingale and with the Dupmeyer decomposition we just mentioned, so that we can decompose this part with m star into something which is upper bounded by the value of the Snell envelope, so that we can get an upper bound of this, and the EVM is achieved when this optimal martingale is reached. So to solve it by numerical solvers to verify this, we use this case to price the 1-year Bermudan put option, which is a special case of American put option that allows for early exercises at set dates. So we use monthly exercise, and this underlying asset follows the geometric bounding motion. And we want to show that the primal price or the lower bound and the dual price or the upper bound converges to the reference value. So the reference value here is given by 5.15. So we can do the following. So first we express the value of the option at time ti to be the VTI. Then, or in dual form, it can be reflected infimum over all this class of M0 naught static expectation, where this is the discretized set martingales. So we can break this optimal martingale as m star, which satisfies 0 as initial time, and this and also this difference of this optimal martingale has very nice proposed form solutions. So we can use a nested Monte Carlo algorithm, so that first we use the so-called Longstaff-Schwarz algorithm, so that it outputs a sequence of optimal stopping times tau I star by using regression problems, kernel regression methods to estimate this CTI hat, which is the continuation value of these options, numerical options at time ti. And then by running this algorithm, we can simulate new independent paths to be able to estimate the martingale increment we described above, so that we simulate P1 paths from 0 to t to get the primal strategy or optimal stopping times. So another thing is that we use this AP algorithm. It outputs the approximated optimal martingale to find this V naught. So it is actually done in 3 steps. First, if this tau I hat indicates continuation, we estimate this quantity. So if this exercise index exercise, we estimate this quantity. If t is smaller than t, we estimate this quantity. Then we compute the approximated martingale m star using some Monte Carlo expression, and we use these 3 plugin estimates, and then we compute V naught hat. And by Python simulation, we see that the primal price is this, and the dual price is this, which is a very nice approximation. Thank you.